Okay, are you able to see this?
Yeah.
Okay, good. Thank you. Good afternoon, everyone. My name is Brooke Misner, as you said. I'm a sophomore at Spring Studio for Academic Excellence, and I am taking college algebra. My presentation today is called COVID-19 and Colorado. What do the numbers tell us? Plato once said that numbers are the highest degree of knowledge. It is knowledge itself. As we journey through unknown territory, I believe that numbers are one of the most important things that we can hold on to. We can find math in the most unexpected places, and we can use the information to determine the best paths forward. COVID-19 was discovered about a year ago, as you all know, and since then it has spread across the whole world to become a global pandemic. But how has it affected our home state, Colorado? Well, we can use math, statistics, numbers, and graphs to gain a better understanding of the effects on our state. Now, Colorado had its first few cases around March 5th, and since then the case number has climbed to over 176,600 cases. The daily case growth is shown in this graph, and we can see that the graph seems to create one that's very similar to that of a logarithm, which is very interesting. This is partially because I used the equation natural log A over B to get this graph when A is equal to the case amount for the current day and B is equal to the cases for the previous day. As you can see, within the first couple of days, the case growth rate was extremely high. This makes sense given that if an initial value is relatively small and it increases by the same amount as another given data point, which is initially much larger, the growth rate would intuitively be much higher with a smaller initial number. In this case, from March 17th to March 18th, there were 33 more cases. If we use our equation natural log A over B, we find that it was an increase of around 16%. However, if we added 33 to the data from November 1st and plugged it into our logarithmic growth rate equation, we would find that the growth rate would be massively smaller at around 0.03%. At first glance, this graph makes it seem as if the cases have gone down dramatically, but this is a mere misleading aspect of logarithmic growth. We can see that the growing rate has not consistently dropped below 1%, which can present a serious problem. The growth rate above 1% indicates exponential growth, whereas a growth rate below 1% indicates exponential decay. An example of this is that if the growth rate was consistent at 1.5%, the case amount would double in just over 45 days. When we're looking at numbers like 176,000, in only a month and a half, we would be well over 350,000 cases, which would be detrimental. Because of the nature of logarithms and exponential growth, it is sometimes more accurate to look at these statistics linearly. This is the graph of the new cases daily. The equation that I used to get this graph is y equals a minus b, when a is still the current case amount and b is still the case amount from the previous day. As we can see, the graph also gives a logarithm-like appearance, even though the equation does not use the logarithm. This gives us a more accurate look at the COVID-19 spread. The graph shows that there was a huge spike in cases beginning around mid-November, and we continue to see the effects of it. Ideally, the new COVID-19 cases per day would be approaching 0 on this graph, but this is very difficult to achieve. In early April, we started to hear the term flattening the curve. This term often refers to a graph similar to the one at right. The purpose of it is to avoid overwhelming the hospitals with sick patients, which would leave some patients without proper care and attention required to successfully overcome the virus. We can see that the dotted line arbitrarily indicates the hospital capacity, and there are two curves. What we want to avoid is a curve similar to the red one. One thing to note is that both of these curves indicate the same amount of cases, which is very important. The only difference is a matter of time and how much time it takes for these cases to pan out. This means that the growth rate needs to be below 1% and the new cases need to be steadily decreasing if we want to get to the other side of the curve. If we have already flattened the curve is a good question that can only be answered with time, as any day could bring about a steep decline or steep spike in cases. Another way that we can observe Colorado's COVID-19 data is linearly with the compound amount of cases over time. In this graph, the blue line represents total cases in Colorado throughout all time, and the red line represents the total death count over all time. You can see that the caseload seems to be pretty consistently rising until recently when we have seen a spike in cases. At this point in time, the cases are increasing steeply. One other noticeable trend on this graph is that the deaths seem to be going at a flat rate in comparison to the rapidly increasing cases. This is interesting because we would assume that the deaths would follow a similar pattern to the cases, but this does not seem to be the case. If we take a closer look at the deaths, we can see another very interesting trend. The deaths seem to also create another type of logarithmic line. They increased quickly in the beginning and have been increasing at a much slower rate recently. It is likely that we're going to see these figures increase in the next couple of weeks given the current spike in caseloads, and of course the death count lags in relation to the case. So the question remains, did we prevent COVID-19 from being what it could be? We will never really know the answer to this question, as there are endless factors that could not all be accounted for at once. But we can look at the information that we have, the numbers, the graphs, the maps, the statistics, and we can decide for ourselves what could have been and what comes next. In conclusion, there are several things I want you to get out of my presentation. First of all, math is the universal language, and it can tell us things about our world that we never would have found otherwise. Logarithms can be found in places that they never would have been expected. They're in growth rates, new cases, and death counts. Second of all, the application of these numbers is up to you. You can decide to use this information however you want. But here are the raw numbers. Thank you so much for watching my presentation. I got all of my information from the Colorado Department of Public Health and Environment website, which is shown on the slides. Any questions?
There are no questions.